Hello students, welcome to EPG Pathshala. I am Sumalay Roy from the Department of Physics and Astrophysics of University of Delhi. Today we are going to discuss about the module Degenerate Perturbation Theory. This is from the paper Quantum Mechanics. So students, let us see what we are going to learn in this module. First of all, we will know why non-degenerate theory does not work when unperturbed states are degenerate. We will learn how the degeneracy is removed by studying a simpler case of two-fold degenerate system. We will learn how a common unperturbed energy levels, a single energy level is split into two when the perturbation is switched on. We will learn how a common unperturbed energy level is split into two when the perturbation is switched on. We will learn to derive the expressions for the energy levels and the corresponding eigenfunctions when a perturbation is applied to a system having R-fold degeneracy. Having studied perturbation theory for a non-degenerate case in the preceding module, we shall now consider its generalization to a system of degenerate energy levels. We shall first see why non-degenerate perturbation does not work for this case. In order to appreciate how a degenerate energy level is split and the degeneracy is removed by the perturbation, we shall first take up a simpler case of a two-fold degeneracy and then turn over to its generalization to a R-fold degenerate system. Now, let us first discuss two-fold degeneracy and how this degeneracy is removed, that means removal of degeneracy. If the unperturbed states are degenerate, that is, the two or more distinct states, which is designated by psi n1 and psi m0, belong to the same energy, the ordinary perturbation theory fails. We see from 27.19 that the coefficient ANL with the subscript 1 is given by ANL1 equals to H prime NM divided by EM0, that is 0th state, ground state, minus EN0. This thing blows up unless the numerator vanishes. In the degenerate case, therefore, there is no reason to believe even the first order correction to the energy, and we need to modify the theory in such cases. Twofold degeneracy. Now consider two unperturbed eigenfunctions, psi n0 and psi m0, which are normalized and orthogonal to each other. And these are the eigenfunctions of the unperturbed Hamiltonian H0, so that H0 psi 1 equals to E0 to psi n0. Also, H0 psi m0 equals to E0 psi m0, where here it is assumed that the psi m and psi n is normalized, that is, their inner product psi n0 into psi m0 is 0. Note that any linear combination of these states, psi 0 equals to alpha psi n 1 plus beta psi m 0 is still an eigenstate of H0 with the same eigenvalue E0. Now H0 psi 0 equals to E0 psi 0. The role of perturbation H prime is to break or lift the degeneracy. As we increase lambda from 0 to 1, the common unperturbed energy splits into two. We can see it in the figure 29.1. As we turn off the perturbation, the upper state reduces to one linear combination of psi n 1 and psi m 0. And the lower state reduces to some orthogonal linear combination. We have therefore to find correction out of this good. We have therefore to find correction out of this good. Now here we have a figure which shows that energy E is plotted as a function of lambda, and on the scale of energy there is a point at E0 where, depending upon lambda, there is a two lines bifurcated till lambda is equal to 1. So this shows the lifting of a degeneracy by a perturbation. That means the point at E0, which was a single energy, which becomes different energies, which is non-degenerate, with increasing value of lambda, which is shown up to lambda equals to 1. Calculating first order energy correction. Good linear combination before we calculate the first order energy. Let us now suppose that we want to solve the Schrödinger equation H psi equals to H psi, where the Hamiltonian H equals to H0 plus lambda H prime and E equals to E0 plus lambda E1 plus lambda square E2 and plus so and so on, and psi equals to psi 0 plus lambda into psi 1 plus lambda square into psi 2 plus so and so on. Substituting 29.6 into 29.5 and collecting the powers of lambda, we find H0 psi 0 plus lambda into H prime psi 0 plus H0 psi 1 plus dot 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 equals to E0 psi 0 plus lambda into E1 psi 0 plus E0 psi 1 plus so and so forth. The first term on both sides gives us equation 29.4. Equating the coefficients of lambda, we get H0 psi 1 plus H prime psi 0 equal to E0 psi 1 plus E1 psi 0. Now taking the scalar or inner product with psi and 0, we have the matrix element of H0 between psi and 0 and psi 1 plus the matrix element of H prime psi and 0 between psi and 0 and psi 0, which is equal to E0 into scalar product of psi and 0 and psi 1 plus E1 into scalar product of psi and 0 and psi 0. Since H0 is Hermitian, the first term on the left cancels the first term on the right hand side. Using 29.3 for psi 0 and using the orthonormality condition 29.2, equation 29.8 reduces to alpha into the matrix element of H prime in between psi and 0 and psi and 0 plus beta into matrix element of H prime between psi and 0 and psi and 0, which is equal to alpha into E1, or writing in the compact form alpha into WNN plus beta into WNN equal to alpha into E1, where Wij is the matrix product of psi I0 H prime or psi J0, where I and J equals to N and M. Equation 29.9 can be rewritten as WNN minus E1 into alpha plus Wnm into beta equals to 0. Proceeding exactly in the same way, we take the scalar or the inner product with psi m0 of 29.7. We get equations similar to 29.11. That is Wmn alpha plus Wmm minus E1 into beta equals to 0. Equation 29.11 and 29.12 are two homogeneous equations for alpha and beta, and they can have the solutions except the trivial one for alpha equals to beta equal to 0 only if the determinant of the coefficient vanishes. That is, determinant of Wn minus E1 first element, the first row second element Wn, the second row first element Wmn, and the second row second element is Wmm minus E1. This determinant equals to 0. This is called the secular equation for the problem. It is the second order algebraic equation for E1. Explicitly, E1 square minus Wn plus Wmm into E1 plus Wn Wmm minus Wmnm into Wmm, which is equals to 0. And E1 is equal to half of Wn plus Wmm plus minus half of square root of Wn minus Wmm whole square plus 4 times Wnm into Wmn. This is the fundamental equation of degenerate perturbation theory. There are two possible values of E1, say E1 plus and E1 minus, and consequently the original energy levels split into E0 plus E plus 1 and E0 plus E minus 1. As a result of perturbation, this splitting occurs. We say that a perturbation removes the degeneracy. It may happen in some cases that for some perturbations E plus 1 equal to E minus 1, in which case the degeneracy is still not removed. Note that for the case alpha equals to 0 and beta equals to 1, we have Wnm is equal to 0. And from 29.12, E1 is equal to Wmm, which is already included as E minus 1 in 29.14. Similarly, for alpha equals to 1, beta equals to 0, we would get from 29.11 E1 equals to Wn, which is E plus 1 given by 29.14. General case of alpha fold degeneracy. General case involving alpha fold degeneracy. Having studied a simpler case of two-fold degeneracy, the generalization of the above treatment to the case of alpha fold degeneracy becomes quite straightforward. Let us assume, without loss of generality, that a set of alpha unperturbed wave functions psi nr0 corresponding to the level En0 are mutually orthogonal and normalized to unity, so that psi nr0 with a scalar product with psi nr0 is equal to delta Rs, where R and S are integers which runs from 1, 2, 3, 4 this way till alpha. Let us introduce the correct zero order function chi nr0, which is the first order term in the expansion of the exact wave function psi nr. So what does it mean? Psi nr equals to chi nr 0 plus lambda psi nr1 plus lambda square psi nr2 plus so on and so forth. We also write the perturbed energy ENR as ENR equals to ENR0 plus lambda into ENR1 plus lambda square into ENR2 plus so on and so forth, where EN0 is equal to ENR0 and R runs from 1, 2, 3, 4 to alpha. Since the unperturbed energy level is alpha-fold degenerate, we can write that. Substituting the expression 29.16 and 29.17 in the equation H psi n equals to En psi n and equating the coefficients of lambda, we have H0 psi nr1 plus H prime chi nr0 is equal to En0 psi nr1 plus ENR1 into chi nr0. Since the function chi nr0 are linear combinations of the unperturbed wave functions, we write chi nr0 equals to sum over s equals to 1 to alpha constant CRS to psi ns of the order of 0, where r varies from 1, 2, 3 this way till alpha, where the coefficients CRS are to be determined. Similarly, expanding psi nr1 in the basis set of unperturbed wave functions, we write psi nr1 equals to sum over k and sum over s equals to ANR superscript 1 into KS into psi KS0. Substituting the expressions 29.20 and 29.21 in equation 29.19 and using the fact that H0 psi KS0 equal to EK0 into psi KS0, we get sum over K, sum over S, A1 NR comma KS into EK0 minus EN0 into psi KS0 plus sum over CRS into H prime minus ENR1 into psi NS0 equals to 0. Taking the inner product, that is multiplying by psi NN0 star and integrating over all coordinates, we obtain sum over K, sum over S, A NRKS 1 into EK0 minus EN0 into scalar product of psi NU 0 with psi KS0 plus sum over S CRS WNU NS minus ENR1 delta US, which is equal to 0. Here U is equal to 1, you can take 1, 2 till alpha, where we use 29.15 and have written WNU NS equals to psi NU 0 H prime psi NS 0 and psi NU 0 and psi K 0 vector scalar product is 0 when K is not equal to n and EK0 is equal to EN0 if K equals to n. We see that 29.22 reduces to sum over S equal to 1 to alpha CRS into W NU NS minus ENR1 delta US equals to 0, where S and U are, you can take 1, 2 values up to alpha. This is a linear homogeneous system of equation for the alpha unknown quantities CR1, CR2 till CR alpha. A non-trivial solution is obtained if the determinant of the quantity in square bracket vanishes. determinant of WNUNS minus EN1 NR1 delta NS equals to 0, where SU can take the value 1, 2 till alpha. This is the secular equation analogous to the one 29.13 which we obtained above for doubly degenerate case. In the determinant form, equation 29.25 is explicitly written as shown in the next slide. So the determinant is 0, where the first element in the determinant is W n1, n1 minus E nr1. Second element, first row, is W n1, n2. Third element W n1, n3 till W n1, n alpha. Now similarly the first element on the second row is W n2, n1. The second element is W n2, n2 minus E nr1. Third element is W n2, n3 till the element W n2, n alpha. This way, first element of the last row becomes W n alpha n1. Second element of this last row becomes W n alpha n2. Third element W n alpha n3, so on, which extends up to W n alpha minus E nr1. This whole determinant equal to 0. This equation is of degree alpha and has alpha real roots, that is E1 n1 1, E n2 1 to E nr1. If all these roots are distinct, the degeneracy is completely lifted or resolved to first order in the perturbation. On the other hand, if some or all roots of 29.25 are identical, the degeneracy is only partially or not at all removed. The residual degeneracy may then either be removed in higher order perturbation theory or it may remain in all orders. For a given value of R, the coefficients CRS for S is equal to 1, 2, 3, 4 to alpha, we determine the correct zero order wave function chi nr0 via 29.20 may be obtained by substituting the value of ENR1 in the system 29.24 and solving for the coefficients CR1, CR2 like CR alpha in terms of one of them. The last coefficient is then obtained upon a phase by requiring that the function chi nr with the superscript 0 be normalized to unity. This procedure gives a unique result when the degeneracy is completely removed. From the discussion given above, it is clear that the determination of the correct zero order wave functions chi nr0 where r is equal to 1, 2 till alpha amounts to finding the proper orthonormal linear combination of the original zero order degenerate states, such that the matrix H prime M M equals to xm equals to chi m 0 H prime chi m 0, where R is equal to 1 to 2 to alpha be diagonal with respect to the indices R and S. The diagonal elements of this matrix are equal to the corresponding first order corrections ENR1 equal to H prime E prime. First order corrections ENR1 equal to H prime NR, where R equals to 1, 2 till alpha. Once the correct zero order wave function chi nr0 have been determined, the first order correction psi nr1 to the wave function and the second order energy correction ENR2 can be obtained in a way similar to that followed from the non-degenerate case study in module 27. It is interesting to note that if all the original off-diagonal matrix element WNR minus is equal to a matrix element of H prime between psi NR0 and psi NS0 when R not equal to S vanish. That is, if the degenerate state psi NR0 where R starts from 1 to till alpha belonging to the level UN0 are not connected to the first order, then the secular equation 29.25 takes the simple diagonal form. What is that? The first element of the determinant is Wn1, n1 minus ENR1. All other elements in the other column are 0. The first element in the second row is 0. The second element is Wn2, n2 minus ENR1. Then 0, 0, all other 0. This way, the last row reads as the first term 0, the second term 0, the third term 0, and finally Wn alpha, n alpha equal to ENR to the power 1 equals to 0. In this case, we see from 29.20 and 29.24 that our initial unperturbed wave function psi NR0 are already the correct zero order wave function for the perturbation H prime. Moreover, the roots ENR of equation ENR1 of equation 29.28 are given by the formula ENR1 equals to WNR minor, where R is 1 to 2 to 3 like this till alpha. If we compare it with our results obtained in module 27, we shall find that degeneracy plays no role in this analysis. This is what happens whenever the unperturbed states are uniquely specified in terms of a set of operators which all commute with the perturbation. In this module, we have learned that to know why non-degenerate theory does not work when. Why non-degenerate theory does not work and when unperturbed states are non-degenerate. We learned how the degeneracy is removed by studying a simpler case of a two-fold degenerate system. We have learned how a common unperturbed energy level is split into two when the perturbation is switched on. We have known how a specular equation is developed. We learned to derive the expression for the energy levels and the corresponding eigenfunctions when the perturbation is applied to a system which has R-fold degeneracy.